Okay, time to get going. So here's where we were last time. So we were talking about this strategic diagram. I didn't have time to go through everything I wanted to say about this, so we're going to pick up and start over on this. So I've previously, I'm in the wrong mode here. Let's see, here we go. Still in the wrong mode. Okay, I've previously talked about putting these operators in this order. This was back in chapter 3. It kind of came out of nowhere. I couldn't give you any justification for it other than, well, there's really good reasons for it. I'm still not going to be able to tell you all of the really good reasons. It's way too much for this course. But I do want to start to show you some of the cool consequences that we can start to see, and we're going to see this develop over time. So here's a reminder of what we've already discussed. This second sequence down here is, I'm going to say, unavoidably natural. If you have a two-dimensional region, the boundary is a curve. If you have a curve, the boundary is a pair of points. That's just what it is, right? That's how boundaries work. So here's the first case I'll make for why it kind of makes sense to put these in this order. You'll notice that the fundamental theorem of line integrals is a statement that relates curves and their boundary points and also relates functions and their gradient vector fields that fits. Right? So just an observation. And then likewise, Green's theorem, right? That was last week or so that we were talking about this. But Green's theorem is a statement about two-dimensional regions and their boundary curves and between vector fields and their curl functions. Right? So again, it's the same sort of a fit. So now you might say, okay, well, that's, okay, so maybe that's an arbitrary, I rigged it up so that it would work out like that. Okay, true. But notice there's another nice thing about this. This is an exact sequence, which means that everything has a lifetime of 2. And again, there's a couple of little exceptions. You got to worry about regularity but let's not get into the weeds. By and large, generally speaking, gradients have curl equal to 0, and any vector field that has curl equal to 0, let's think about that for a second. If the curl is 0, that means it's irrotational, which means it's path independent and a gradient. Right? So we now can see in some sense why this, again, the term that we use to describe this scenario is exact. Why this sequence is exact, which is, again, kind of an eyebrow raiser. And any one of these observations by itself, you could say, well, you just kind of arranged it that way. But the fact that we've got 2 good reasons, I think that's starting to get more compelling. And there's more reasons. We're going to see this observation really magnified over the next couple of weeks as we go through chapter 7. But I want to just show you the tip of the iceberg here so far. We've already talked about how we have these 3 different properties of vector field being a gradient is, again, all exceptions granted. You got to worry about singularities and regularity. They're pretty much the same as the path-independent vector fields. Totally different property, same vector fields. Which is also totally different property, but the same vector fields as those whose curl is 0, namely those that are irrotational. So how does this look on the diagram? I'm going to switch over to a cleaner, sort of fuller copy of the diagram that I like to use. By the way, this document here is available to y'all. If you're interested, you go to the class website, you click on class materials right here, and there it is, diagram.pdf, in case you want a copy for yourself. How would I represent on this diagram that I have a vector field? Let's get into the right mode again. Okay, a vector field. How would I describe that it is a gradient of something? I'm going to do it like this. I'm going to say there is a function whose gradient is that vector field. Seems like a reasonable way to represent that. How would I represent that it's irrotational, that curl is 0? And you can see how old this diagram is by the fact that I was still calling curl by GRN. I like to think of it as Green's operator. Anyway, it just means curl. Curl is 0. Looks reasonable to represent it on the diagram like this. How would I represent path independence? Okay, this one's a little different, a little bit weird. I have to say that when I have two curves, very importantly, two curves that have the same starting point and the same ending point, in other words, therefore the same boundary points, that they give the same value of the line integral. All right, so that's a little bit of a weird look, but there's something to be said for noticing that these features lay out on the diagram in a certain way, and there's a preview now of how we're going to capitalize on this. Another hard thing to see coming, but there is a three-dimensional version of this diagram. It's going to be much of what Chapter 7 is going to be about. And these three properties of vector fields in 2 dimensions, vector fields of which you're interested in line integrals, these three properties, they actually translate amazingly. It also works down here for vector fields in R3. Same exact pattern. And here's what blows my mind the most. You can also move over to the right. You can increase the dimension. And let me zoom in now so we can see more clearly what's going on here. We can talk about vector fields of which we will be interested in whatever this critter is. We haven't even talked about that yet. This is going to be something called a vector surface integral. We haven't gotten there yet. We'll be getting there probably Friday. We'll start to tip of the iceberg today. But there's a special collection of vector fields of whose vector surface integrals we're interested in that have the same sort of like trio of properties. All the same vector fields have all three of these properties. They're all simultaneous, regularity issues aside. Those that are curls have divergence equal to 0 and are, well, let's see, this is, what would we call this? This is kind of a surface equivalent of path independence. How about we call it surface independence? All of this is going to fit. All of this is going to make sense, even though everything in sight is dimensionally different. We're not talking about curves and their shared boundary points. We're talking about surfaces and their shared boundary curves. Everything one dimension up. Right? And again, this on the left, this operator on the left, that's not gradient, that's now curl. This is no longer curl, now it's divergence. Everything's different, but the pattern's the same. That's a shocker. Right? So I am a tremendous fan of understanding these ideas in the context of this diagram. I use this diagram a lot when we get into Chapter 7. We'll be spending a lot of time working with this diagram. There are several reasons for it. The most immediately beneficial, the most immediately persuasive, I think, argument for y'all is that this will help you with seeing and understanding analogies. Things that make sense in one context, shift everything over on the diagram, and that's going to help you understand how it makes sense in that other context. Noticing patterns, noticing diagrammatic patterns will help you remember facts. You don't have to remember multiple different theorems. You only have to remember one pattern on the diagram. And those patterns are most visible, in my opinion, on this diagram. And the other reason I'll just give you real quick as to why I like this. Y'all may recall that I've been making allusions to the more sophisticated take that we can't really do in this class. It's just too much. It's heavy machinery, lots of abstraction, sophisticated modern mathematics that wasn't even known until less than 100 years ago, right? Very recent stuff. That's where this diagram comes from. I took some sophisticated, advanced machinery that we're not ready to talk about, and just kind of boiled off all the formalities and, cut to the quick. How does this manifest in situations that we're going to be dealing with in 2 and 3 dimensions? This is what comes out from that, right? So this is a glimpse. This is you're seeing kind of, you might say, shadows of some very sophisticated and powerful mathematics. That's what this diagram deep down is and where it comes from. So that's kind of cool. Okay. All right. So that's all I'm going to say about that. And we move along now to paying off on a promise that I made some time ago. Let's see. I guess it would be it might have been last time. I can't remember. It might have been Friday. But we talked about how do you find an anti-gradient, right? I showed you an example of using the fundamental theorem of line integrals. I pulled the anti-gradient out of a hat. Promised I would show you how to find them. Here we are. Okay. So, you've got some vector field. You would like to know how to find the anti-gradient. Keep in mind the anti-gradient is that function. It's the thing whose gradient is that vector field. So another way to say this, if you want to find an anti-gradient, you have to recognize the vector field as being a gradient. Said differently, you need P, Q, and R to equal to these partials of a single function f. In other words, you need these 3 equations. Okay, that's just kind of framing the question. Okay, how can I argue, or how can I rephrase the statement that the x partial of f is equal to p? Well, how about this? I'll say that f is the x anti-partial of p. Same statement pretty much, right? It's kind of grammatically, like passive tense instead of active tense. It's kind of the same statement, right? Okay, now there's a little subtlety involved in this, and that is the c, right? Y'all are accustomed to saying plus c whenever you do an antiderivative. And reminder, why is that? Well, because when you take this statement and turn it back into that statement, what you're doing is you're going to be taking a partial of both sides with respect to x. And anything, when you take the derivative and get 0, is free. And therefore you can and therefore kind of have to put that plus c because you don't know which antiderivative you're actually looking for. So we have to say plus c in recognition that I don't know what this might be. So the observation to make here is that we are no longer looking at single variable calculus where the only time a derivative is 0 is if it's a constant. We're looking at a partial derivative. So we have to ask the question, what are the functions whose x partials are 0? And, well, there's more than just constants. There's what we call partial constants. Any function of y and z only. Any function that doesn't have any x's in it. You take the x partial, it gets 0. That means it doesn't cost anything. You kind of have to put it in there so you're not arbitrarily, for no reason, narrowing your search for the antiderivative. Does that make sense? Is everybody on board? It's kind of a partial derivative equivalent of an integration constant. Yeah?
Does C also include, like if you just had a 2?
Yeah. Because 2 is a boring and yet still function of y and z. Yep. Does that make sense? Yeah. Okay, so likewise for the other variables. And so here we are. Here's our requirement. If you would like to know the function, a function that is the anti-gradient, well, it has to be that. Well, let's do it like this. It has to be this, but it also has to be that, but it also has to be that. We're looking for a function that is all 3 of these things all at the same time. A single function that satisfies all of these requirements. And so write it down. Get started. Play the game. See if you can do it. That's the method. It's not so crazy. Here's an example. Got a vector field here. I want to find the anti-gradient. I want to find the function whose gradient is this vector field. Well, okay. I need to take the x antipartial of that, the y antipartial of that, and the z antipartial of that, right? That's just following the rules of the game. That's what we already agreed to. So here I go, right? I'm going to write down those antipartials. And the first part of those antipartials, of course, is easy, right? I mean, coming up with all of this stuff here, that's a pretty big yawn. Just don't forget, you got to make sure to remember to keep track of which variable is the variable. Don't forget the other two variables are constants. Treat them as such. Right? So it's easy to kind of whoopsie and take the wrong antipartials. Then we have to acknowledge, I don't know, it could have some function of y and z added to my x antipartial, and likewise function of x and z, likewise function of x and y to the other antipartials. So don't forget to add those in. And the game has begun. Can we find a function that is simultaneously all three of these things? Now, let me show you how I like to play the game. Right, this is whatever. This is just my personal preference. I see this x squared y and that x squared y, and I feel like, okay, you know what? F probably has an x squared y in it, except unfortunately, wait a minute, no good. It's got to be all three of these things. So if I claim that there's an x squared y in the answer, then there's got to be an x squared y in this third line, and I don't immediately see an x squared y, so what's up with that? Well, the answer could be maybe that is x squared y. I am, after all, allowed to put any function of x and y in here. This is how I play the game, right? I get to pick what these integration partial constants are. So how about I just say, you know what, I think that's going to be x squared y. How we doing? Is that good so far? Right? Still haven't won the game, but we're in the game at least. And then I see this, and I figure, hey, maybe this is xz also. Okay, so cool. And then I see this, and then I figure, hey, maybe that is minus yz squared also. And you know what? We just won the game because I have found a function that is equal to all three of these required forms. We win. And you can check for yourself, and this is a good, healthy exercise. Everyone should do the following. You can check for yourselves that this function that I claim is the anti-gradient, if you take the gradient, x partial, y partial, z partial, indeed you get what you need to get. How we doing? Everybody okay with that process? It's nice and algorithmic. Careful of the details. Okay. All right. So now we knew we were going to win that game. We knew there was an anti-gradient because you can take this function, you can compute the curl, a little bit of algebra, no big deal. But you can compute that curl. You get 0. You know there's an anti-gradient. This game is rigged for us to win. What's it look like when we can't win the game? What's it look like when there is no anti-gradient? Well, let's look at this vector field. Now, we've already looked at this one. We've already computed the curl. We've already seen it's not 0. So we know there is no anti-gradient. So this is a wild goose chase that we're about to enter into, right? We're trying to find an anti-gradient that doesn't exist. All right, so how does it go down? Well, I'm going to play the usual game. We're going to take the x antipartial of the first component and then the y antipartial of the second component, and you get these, and then you don't forget to add your integration partial constants. And again, the game begins, and we lose. There's nothing you can do here, right? It's just not going to work. And you can try. It's not going to work. Everybody good? Okay. So strategically, how should you do this? Should you compute that curl first so that you know whether to play or not to play? Or should you just go ahead and start playing the game and then just kind of trust your intuition to, oh gosh, this looks like a loser to me. I don't think I want to play this game. Well, there are some questions there, and it depends on the situation. It depends on how hard will it be to do those anti-partials. How hard might it be to compute the curl, right? There's no single answer on that. But those are your tools, and, you can play the game however you like. Yes?
So when we're trying to find the anti-gradient, are we, how many terms should match up?
All of them. So F has to, if you're going to claim that you have an anti-gradient, it has to equal to all three of these things. And so that means that all three of these things have to be equal. And so any term that's in two of them, well, again, all three of these things are equal, so it also has to be in the third. Does that make sense? Yeah. Anybody else? All right. Moving along. So that does it for chapter 6. On to chapter 7. In chapter 7, we are going to talk about, let's see here, we are going to talk about this new construction. Oh, whoop, again, wrong mode. We're going to talk about this new construction. This is called a vector surface integral. We're not quite ready to do that just yet. Let me remind you, we spent some time talking about vector line integrals. Before that, scalar line integrals. And one of our primary tools for understanding those was parametrizing the relevant curve, right? The domain, what was going to be the domain for those constructions. Well, here we are again. Before we can really be ready to understand what this is, we need to talk about how to parameterize this domain, this being a surface. So how to parameterize surfaces is actually going to be our very first thing to do here. Okay, good news. We've already done one of these. I didn't use the term back then, but all a parametric surface is position, rectangular coordinates position, as a function of two parameters. A parametric curve is where you have position as a function of one parameter, and it literally traces out a curve. You can think of that parameter as being time, and it literally traces out the curve. Here we have two parameters, so sadly we can't really think of them both as being time. Again, we get into some weird, probably entertaining, but weird science fiction movie kind of nonsense, right? So don't go with the time metaphor, but it remains, I just need position as a function of two parameters. And here's the example we've already done before, right? We've talked about if you give me a point and two direction vectors, and if you say, I would like to be able to construct all of the points in this corresponding plane that goes through that point, parallel to these two direction vectors. If I want to construct position on the plane out of those things, then what I do is I look at all convenient multiples, possibly convenient multiples of those given direction vectors, add that to the given starting point, and I get position by that little expression right there. And then you notice, oh my gosh, each one of these terms over here involves a new parameter. So in fact, I have position as a function of two parameters. Now I did that quickly because again, we did this argument back in chapter 1, way back long ago, right? Section 1.5. I think there was a homework exercise that was heavily motivated by this, right? So anyway, that is in fact our first parametric surface, position as a function of two parameters. Okay, and you can see the roles that the parameters play. The S parameter, what it does is it tells you in some sense how far we're going kind of that way. Right? And then analogously, you can see that the T parameter, what's its role, what's it doing sort of geometrically? Well, it's sort of telling you how far we're going that way. Okay, so we're just going to see some more examples. Here's my favorite, graph parameterization. You remember this is also my favorite curve parameterization technique because it's so easy when it works, right? It's totally awesome. Likewise for surfaces. Anytime you have a graph, notice this equation is a graph. We've got z as a function of x and y. It's the same trick. It's the exact same trick. Whatever are your input variables in viewing your surface as a graph, let those be your parameters. It's just like with parametric curves. Does everybody remember graph parameterization for curves? Totally analogous. The rule there was let the input variable, singular, be your parameter. The rule here is let your input variables, plural, be your parameters, plural. Okay, so easy example. Here is a surface. Notice it is a graph. X and Y are my inputs. So I let X and Y be my parameters. Everything else is already effectively determined for me. I just have to sort of notice that, well, if X and Y are S and T, then it must follow that Z must be S squared plus T squared. Is that cool? Yeah. Mm-hmm.
If it's literally a direct transition, why is it useful?
If it's what now?
Like because S is literally equal to X, why can't you just keep it as?
Yeah, I mean, there's a little etiquette question of if I were to write this as let's see here, R of X comma Y equals X comma Y comma Z, then I have technically a confusion of variables problem. X is both an input and an output. You remember we had problems with that when we were talking about the chain rule. Now, that doesn't mean that you will always have problems, and there are plenty of people who don't feel the need to do what I like to do here and invent S and T. And that's okay as long as they trust that they will be able to see it coming before any bad things happen. And I just don't want to put that level of responsibility on students, and so I'm going to say I'm freeing you of that responsibility by not confusing my variables in the first place, and I think this is a little healthier. Does that make sense? Yeah. Very reasonable question. Okay, so parameterization done, right? We started with an equation for the surface. Now I have a parameterization, position as a function of parameters. And we're going to be able to do really cool things with parameterizations. Notice it doesn't have to be X and Y that are your inputs. Let's look at this equation right here. It's not given in the graph. You can do a little bit of algebra, though. You can, maybe the first thing you'd want to do is try to solve for Z because, alphabetical order and all that. Right? Kind of accustomed to solving for Z. And then you try to solve for Z and you realize you can't. Right? You're algebraically tied up. Right? You can't do that. Likewise, you can't solve for X. But you can solve for Y. And now What are my input variables? Right now that I have it written as a graph, I have one of the variables as a function of the others. What are my input variables? Well, this time the input variables are x and z. So I'm going to let those be my parameters, s and t. Just follow me the rule. Right? Let x be your parameters. Let the input variables be your parameters. And again, game over. It's just a matter of realizing it. If, in fact, x is s and z is t, then it immediately follows that y has to be that. And again, we win. Now I have a formula that gives me position as a function of s and t. Is that cool? Everybody on board? It works with other coordinate systems. All of what we're doing here, again, by the way, is very analogous to what we saw with parametrizing curves. Right? We saw an analogous example with polar coordinates in, section 1.1 or 1.2, right? Super early. It's been so long, you might want to check back in the notes to remind yourself. Make sure you remember it. But same deal here. All you have to do is just don't forget to do your conversion. Right, so there's my standard conversion formula. If I have spherical coordinates and I want rectangular coordinates, boom. Right? So you just write that down, and then if you have what you might call a spherical graph, here we've solved for rho as a function of phi and theta. It's a boring function of theta. That's okay, right? But rho is a function that depends on nothing other than phi and theta. Not even theta. Perfectly fine. Then again, you just kind of plug that in, right? So put the formula for rho where it sort of has to be, right? And again, check it out. We win, right? Again, we have now position, rectangular position, functions of phi and theta, so two parameters only. I didn't even have to make up new variables here because there was no confusion of variables potential, right? I don't have x as both an input and an output, so I can just leave phi and theta. Frankly, I kind of like leaving it as phi and theta because then I have this visual reminder of what role is each one of these parameters actually playing. Okay. All right. Okay, this next example, it's one of these, I'm sad that I can't go through, spend time on this example. You could take a look if you like. This is a little bit obscure. It doesn't really come up very much, but do y'all remember, back with parametric curves, we talked about the bicycle wheel with the reflector on it, right? And it's kind of this weird, use vector algebra, break a hard problem into two much simpler problems, a lot of details, right? So this is kind of the two-dimensional version of that. This is the surface parameterization equivalent of that, to view a point as a sum of simpler vectors. And you're welcome to take a look. You don't have to. It's not expected. But we just, sadly don't have time for this. And again, it doesn't come up very much. So no worries. This one does. This, I think, is a very important technique. I've used this a million times in my life. So, suppose I want to parameterize this surface. Donut. The surface of a donut, that is. How do we parameterize that? How would I write position on the surface of the donut, called a torus, by the way? Position on the torus in terms of two parameters. Here's the big idea. Imagine that this is like a weird shaped planet or space station or whatever. Use your magic. Have fun, right? But some sort of a thing where you're going to be spending a lot of time and you need to just be able to describe where you are in the most convenient way possible and create a coordinate system that makes the most sense for that context. Now, real quick example. Y'all know an obvious example of this already. Surface of the earth. Right? Surface of the earth, that's where we live. On the surface of the earth, do we describe where we are by describing our x, y, and z coordinates in space relative to the stars and the sun? Oh, right? Nah, come on. That would be incredibly inefficient. We have this whole longitude-latitude thing, and it just makes sense. It's a natural, sort of geometrically tailored to the circumstance way of keeping track of where you are on the surface of the earth. So that's what we're looking for here. Geometrically, what would be the most tailored? If we lived on this planet, how would we describe where we are on the surface of the planet? And there's different choices on how to do this. This is the one that I think makes the most sense. I would imagine sort of a, if you will, kind of equator going around like that. Right? And wherever you might happen to be, we could talk about this angle. That, I mean, it's kind of an analog of latitude. How far, sort of, you might say in the vertical direction, how far, that way around the donut? By what angle from the center of the doughy part of the donut, by what angle do you go sort of up from the equator? What do you think? Is it reasonable, right? I mean, that's natural for given the geometric circumstance that we're in. And then the second thing I would talk about is, okay, then how far do you go sort of around what you might call horizontally? What is that angle? And let's say measured off of the z-axis. And with these two coordinates, it'd be pretty easy to describe any location on the surface of the donut. Does that make sense to everybody? I tailored it for the circumstance. It's not always going to be like this. We're not always going to be trying to parameterize a donut. Sometimes you might want to parameterize like a cylinder. Geometrically different scenario. You would come up with a totally different natural coordinate system, naturally tailored to the geometry. So anyway, this is what we've got here, and at this point, it's just a matter of looking at an arbitrary point, right? And let's see, what did I think I called this R. We'll get to it there below. But describe the rectangular coordinates as being functions, some function of two parameters, or two coordinates, S and T. So we just have to do some geometry and a little bit of trig, a little bit of linear algebra, play the game, but we just need to figure out position as a function of these new coordinates. You're going to use the coordinate system that you created. Those are going to be your parameters. Yeah.
Sorry, we're only parameterizing by the angle off the x-axis and the angle about the z.
Yep.
Like, could we be 1 inch away from the origin or 12 inches away?
I understand, but do keep in mind that we are talking about just the surface of the donut, though, right? So once I know that you're talking about that angle, and let's suppose we also know that S is 0, let's just say, just for the artistic convenience. So there is, in fact, only one point there that's actually on the surface. So it's implicit that you're on the surface. We're capitalizing on knowing that it's on the surface. And by the way, analogous to planet Earth, right? When we describe longitude and latitude, yeah, well, and of course I mean the point on the surface that has that longitude and latitude. And technically, if we were, 2,000 miles down into the magma, that technically would have the same longitude and latitude. That's not what we're talking about. Is that satisfying?
Yes.
Everybody happy with that? Okay. So here's some geometry, and this is details for y'all to think through. Again, good exercises. Make sure you can do this, but that vector, I better go into pencil mode here. This vector here, you can persuade yourself is that. This vector here, you will notice has to depend on the angle there. It has to depend on that t, and it's a little trig problem, little analytic geometry and trig problem. And make sure you can do this. Make sure you can persuade yourself that that green vector is this, that blue vector is this as a function of t. And so that is sort of the first part of the problem. That tells us where this point is. We're, however, of course, interested in that point. I need to know, not just given a t, but given a t and an s, where is this point? And you see that what I'm interested in, this purple point, is a rotation around the z-axis of the orange point we just wrote down. So we're going to have to talk about how to do rotations, right? And again, flashbacks. So this is a linear algebra thing, right? But how do I rotate around the z-axis? Broad strokes, super quick, because we've talked about it many times. Rotations are linear transformations. Linear transformations are represented by matrices. In a matrix, the columns are the images of the standard basis vectors, right? All of that, the usual sort of ideas, and you can determine these columns one at a time, and there's your rotation matrix. So, putting it all together, let's see, this will work. So, we wrote down the coordinates of this point P, and got that. We talked about how to do a rotation. We got this, and that rotation of that orange point gives us the position that we actually want, and you can multiply this out, and it gives that. So, lots of details, right? Good exercise. Think it through, right? Make sure you're comfortable with all the steps in this process. There are significant details. Again, you got to make sure you're good with those details. The big picture was the simple idea that we're going to just create a coordinate system. Let me go back up to here. We're going to create a coordinate system. Let me highlight better. Okay, oh my gosh. Okay, hang on. We're going to create a coordinate system that makes sense on our surface, given the peculiarities of the geometry of that surface. And then we're going to solve for position as a function of those. How we doing? Everybody all right with that? Okay. Here's another one. And another ripoff, by the way. Another shameless ripoff from Chapter 1. Sometimes you have an existing parameterization, and you can tweak it. And this works really well sometimes. So, for example, let's look at the unit sphere. Now, the unit sphere is super easy to parameterize. In fact, quick observation, if you view the unit sphere as being a graph, a spherical graph, rho is a function of phi and theta. Boring. That's okay, right? Rho is a function of phi and theta. And plug that into your conversion formulas, and you instantly get this parameterization. Right, so this is a good sort of like organically arised graph, spherical graph parameterization. Make sure to think through those details. And I can write, of course, keeping in mind that R is X, Y, Z. Another way to write this parameterization is to write these three equations. It's just alternative form. Okay. So, this all being given, this was easy because the sphere is so geometrically nice. Rho equals 1. Oh my gosh, that's awesome, right? Super convenient. How, then, would I parameterize this ellipsoid? Given that I know how to do the sphere, how would I parameterize the ellipsoid? So, big idea. Again, we're going to tweak what we already have. We already know the green one. And I can kind of see this coming, right? I mean, I'm just, the relationship between the sphere and the ellipsoid is just that, I've stretched by a factor of a in the x direction. and by a factor of b in the y direction, and by a factor of c in the z direction. Right? Again, there's all that old chapter 2 stuff. Right? So, by the way, I've made this observation before, but this is a good opportunity for a reminder. This class is very vertical. Right? So the later material depends very heavily on that earlier material. Right? So make sure that you have a firm foundation. Make sure that you're good to go on all that older stuff. It's unavoidably going to keep coming up, at least here and there. Okay, so, this right here says, look, I need to stretch by a factor of a in the x direction. So look how easy this is. I'm just going to take my wrong color. I'm going to take my existing formula for x, and I'm going to stretch by a factor of a by multiplying all those x coordinates by a.
Why would it be over a? Because
I'm multiplying the formula. I'm not replacing the variable. So it's algebraically a different move, right? So I'm not taking where I had the character x and erasing it and replacing it with x over a. This x is on the left side of the equation here. So I'm not replacing that x. What I'm doing is I'm taking the formula for that x. I need these values to be a times as big. So I literally make them a times as big by multiplying the formula by a. Does that make sense? Look, okay, here's the contrasting point of view. The contrasting point of view would be to take this formula and then, just as you described, replacing x with x over a to get this new formula. And so here, it is x over a because I'm replacing what had been the x with this new different thing, x over a. But notice it's morally equivalent. This a will then just multiply to the other side, and effectively I get the exact same thing as that. Is that cool? Yeah. So it's a great question, by the way, and everyone should spend a little time struggling with this and thinking it through and making sure that you see how two different points of view kind of smacking of each other, easily confused, easily conflated. Make sure you see the differences. See how these are effectively accomplishing the same goal, but by two different sort of points of view. Okay. All right, so likewise for the y's and z's, and based on what was convenient to create for the sphere, we get an easy deformation that gives us a parameterization of the ellipsoid. Everybody happy? Okay. All right. Okay, so let's see here. We got a couple minutes here. So there are several more examples in the book. I do encourage you to look at the book's examples. This book, though, has the same, what I'm going to call shortcoming. It's a disappointment to me, but maybe that's a better term. But I think this is a shortcoming. All of the examples in the book start with a parameterization and then ask what is this parameterizing? And in my experience, that's not how you need parameterizations. My experience is, and I think you're going to find the same thing, you start with the thing that you need a parameterization of. Most things don't come pre-parameterized for you, right? And so you have to figure out how to create the parameterization. You'll notice all the examples I showed you, we created the parameterization. So, yes, there are some cool examples in the book, but they don't show you where they got them from. They just confirm that they do what they claimed. Anyway, so it's, I think, a lot less useful. And let's see, I guess, do I have... Okay, real quick, we're just not going to talk through this next page. If y'all want to get a jump start on Friday's lecture, we are going to go lightning fast through this. I'm basically just going to point to the punchline, but if you want to read this in advance, again, it just doesn't quite rise to the level of justifying use of class time. But it is stuff that you need to at least have a reasonable understanding of, so take a look at that as well. And I'm going to draw the line right here. See y'all later. Have a good rest of your Wednesday.
Thank you.
Yeah.